like any.
That's true. I never have either.
Oh, Sam.
Just kidding.
It looks tricky. Okay.
Any questions before we get started?
Are we going up to the observatory for lab?
Not today.
Okay.
We will not have the capability to do that yet. But probably you, I'm you. We'll get to leave at 5.
We'll wait one more minute, then we'll start. 30 seconds, actually.
Then you just gotta lock the door.
No, I just start. People don't come on time, then they miss the beginning, right? That's the point of recording the lectures, right?
Just lock.
If you showed up to work at exactly 9 o'clock, that's good for you, bad for capitalism, right? But also, you're not really ready, right? You need to sit down, you got to eat your snacks, right? So you show up late, I don't know, you're missing.
Yeah.
This class in particular meets once a week, right? So you can't make it on time.
Not good.
Not good, right? All right. So let's start talking about what you hopefully have read the syllabus. I'm not going to go through it in a lot of detail, other than to note that there were welcoming questions. And the most important welcoming question is the fact that this is not senior thesis. And yet you may need senior thesis. So you were told to take observational astro instead. And you're like, I don't know what astronomy is. Right? So that's okay. We're going to do. This class is primarily going to go back and forth between two different topics. We'll talk about your scientific literacy, your ability to read papers, to understand what's in them. And then at the same time, we'll talk about how telescopes work, how to take observations. And while you're thinking to yourself, well, I won't really ever need to know what a telescope is because I'm going to go into experimental physics, or I'm going to go into like condensed matter. The idea is that some parts of understanding, say, the data analysis will be helpful. So for example, we'll talk about what it means to get some certain number of photons down. And there will be a process in there that you might not be familiar with. But afterwards, you'll do a little bit of computational on it, right? And you'll learn, okay, here's how you centroid these things, or here's how you find the uncertainty on an observation. Those things are helpful. So if you're thinking to yourself, I completely do not want to participate in the astro part, that's fine. I have your name in the welcoming questions. If you haven't filled that out, fill that out. Yeah, fill that out.
Right now.
No, one of the other 2 times that I asked you to. Because you're also in this class, right? Did you fill out that one? No, you didn't. I can tell. I can see all the answers. Okay. And so the idea would be, if you're a physicist and you really, really don't want to do an astro project, that's totally okay. It's going to be a little tricky. You know, obviously there's 12 of you. Well, there's 7 of you here. And the idea is that, you know, we would put a few of you and you would do your own physics project, probably supervised by a physicist in the department, right? Okay. So today what we're going to do is we're going to jump into the subject matter associated with reading and writing scientifically. And then in the lab, for the folks who will not be doing the physics project, for the ones who are interested in the telescope project, we'll learn how to run an EV scope on your own. And you'll notice that, right, this meets for a really long time. Okay, this is like a placeholder. In general, we would not be spending all of our lab time, right? Because that's just crazy. Sun doesn't even go down, right? It's really hard to take observations when the sun is up. In fact, some would say that it's dangerous. Okay, so generally speaking, you have to be thinking about the time commitment associated with the units of this class. So you're not thinking, oh, this is a really cool seminar where I just listen once a week and then I go home and I do nothing for 15 weeks, right? It's a self-motivated class. It'll require writing. It'll require editing. It'll require a lot of work outside and finding times to meet, either one-on-one with me or with your partner, who will set up partners throughout the semester, working on your individual project, revising the data analysis, revising the proposals, editing other people's proposals, etc. Okay. Okay, questions? Okay. No more questions. All right, who knows how to read? No, just one? Okay, over the summer, I know that you can lose some things. So we want to make sure that we understand, the basics. So I'll venture to guess that almost everyone knows how to read, okay? But almost no one knows how to read a scientific paper. And that's okay. This is what the class is for. Okay? We did this part for the most part. We'll talk a little bit about the schedule for the semester. That's the going back and forth. We'll have some check-ins about your progress. You will be finding a topic that interests you, and I'll show you kind of the outline of that as we go through the semester. And we'll do check-ins just like we did with fluids. If you haven't taken fluids with me before, look at the ungrading policy on the syllabus. This is particularly important for this type of class, where it's kind of meaningless to get an assignment back and you get like a 60%. Like, well, I don't want to fucking edit that because it's already in the bin. But the idea is that you make it better, and you make it better, and you make it better, and you turn in something that you're really happy with. And you're like, wow, I'm such a good scientific writer. Right? Okay. And today we're going to read a scientific paper. Okay. This is that scientific paper. So can we pass these out? You're not going to read it right now. I'm going to talk you through how to think about reading this. This is a topic about the atmosphere of Mars. And we're going to get into that. Don't start reading it. You can look at the pictures. Don't start reading it. Topics of today's class is just reading and writing scientific papers. And proposals. We'll talk about proposals a little bit later, how to judge them, how to think about them accurately. Eventually, we'll talk about charge coupled devices. Anyone know what that is? Charge coupled device. Anyone ever seen one? Anyone holding one? Yes. What about the phone? The battery is not a charge coupled device.
I'm thinking of deal with the vectoring. Camera lens.
The camera, not the lens.
Oh, camera.
The camera is a charge coupled device. So what it will do is it will take in light. Light here is shown as little drops of rain. And if you've ever noticed that when you print out a picture and you zoom in, it looks like a bunch of squares. That's because it is recording how much light every square got. Just like if you had a bunch of buckets on a field and you saw how much every single bucket got, you would say, okay, I kind of know what the rain looked like. It's a weird analogy, but it's one that we'll have to go back to in order to understand how a camera works. Because at the end of every modern telescope is not an eyeball. It's a camera, right? Those Hubble telescope pictures, it's not some dude with an eye and then he's like, oh yeah, Bob, this is what it looks like, right? It's a picture and they send it down from space. So we want to understand how charge coupled devices work and how this innovative technology is used both in space and on the ground and what the limitations are. Okay. I think that's it. Oh yeah, we'll do that a little bit too, but maybe in the notes, I'll like revise this. So we'll just do like observation type things. Okay. Okay, so let's sort of brainstorm together. How would you write a scientific paper? Or how would you read a scientific paper? What's the most basic thing you have to do? Yeah. Okay, maybe you can't answer any of these questions. Actually, Reed does research with me, so he's gonna have a even before you can look at the pictures, you have to do one thing. Yeah. Very good. Okay. So even before you do that, you have to do one thing. Get the paper. And that's going to be a step, right? Because if you think about what we know on a day-to-day basis, right? I'm not like walking down the street and people are handing out papers. Read my new list, right? That doesn't happen. So we have to know where to look. And we have to understand what does a good paper look like just from sort of the peripheries. And then the first thing that you happen, yeah, you read the title. You might read something else as well.
Like the journal.
The abstract. Right, the abstract is important. What is an abstract?
Yeah.
Exactly.
It's got all the important bits.
It's got the good bits in it. Right? It's a quick one. Right? It's like a 5-minute summary that you can just spit out, and then someone reads it and go, "This is worth my." Okay, then you read the figures. That's a good idea. Anything else you should read?
Like if they have like a discussion section.
Okay, maybe the discussion of the results. Anything else you should read? Conclusion. Okay, I'll call that part of the results. Yeah. You like the whole thing. You want to go right into the paint. Okay. Anything else?
Introduction.
Oh, yeah. Okay.
Oh,
Someone
it's-
like you like the introduction. That's a separate part than the whole thing, but I'll take it under consideration. Okay, is that it? Are there any other pieces to a paper?
Sometimes this-
What's that? References, yeah, references might be helpful. What would that be? Accreditation, right? If there's no references, that's a pretty big red flag. If the references are all the same person, that's also a big flag. You know, right? When people email me, which happens constantly, and they say, "Listen, I've been able to combine quantum gravity with quantum mechanics and loop theory. And if you just look at my 675-page paper, you'll notice that all of this work that I've done for the past 25 years is going to show it." Like, what did you reference? Is this only your papers? A big red flag. Okay. So this is my idea. This never works. I hate this. Okay. This is not a hard and fast rule, but this is the way that I like to break it down. Okay. First thing that I'm going to do is I'm going to find a paper. And we'll talk about that process. Then you read the abstract. I should also write the word title. You know, sometimes people don't have very fancy titles, but sometimes they have really good titles. I have a friend who is writing a paper or just published a paper, and they are looking at how dust in the lower atmosphere of Mars has different scattering properties, like trying to figure out how that all works. And the name of this paper was "Another One Derives the Dust." I was like, "Damn, Kyle, we're ready."
Random question. What coffee is that?
This is coffee,
Which
iced. Yeah, this is I don't know. It's whatever coffee, like vanilla.
Oh, okay.
It's not special. Okay. Then you look at the figures. Why the hell would I put the figures first? We'll see in a second. Then I say read the conclusion. That's weird. That doesn't seem like the way that the paper's laid out. And then you read the intro and the remainder. Okay? And we'll go through all of these different pieces. The references are actually here. In the first one. Here. You definitely want to check to see if they referenced you. That's how you know. You're like, yeah, awesome. I'm gonna read this one. Okay. So this is a skill. And it's a skill we'll hopefully develop over about 15 weeks. You're gonna go through the process of learning to read your own papers, especially in a field that's different from your own. You may run into issues. You may find yourself in a type of paper that is overwhelming or that you don't really understand, and you might not know when to back away, right? So understanding when to stop reading a paper is just as important as understanding how to read it. Okay, is there a better version of this same paper? Is this something that is written in the 1960s and since then has been completely overlooked, right? Or sorry, overhauled. Okay. Oh my God, almost killed myself. Okay, how do you find a paper?
You use like Google Scholar.
Okay, couple Google Scholars. Friends?
Yeah. No.
I don't have that many friends, so that's not gonna work for me. I need a long-term solution.
There's like I'm almost positive, I can't remember the exact name, but there's like a site that is now being open for like other sciences, but it was originally for like astrophysics. I'm trying to remember the name of it. But,
NASA ADS.
yeah, NASA ADS. There you
Yeah.
go.
So there's other sites like this. There's stuff called like ResearchGate.
That's
There's plenty of sites to find papers on. Some of them they will host to the preprint. So let's say you're at home, you're not logged into the university website, and you can't get the original paper. So they want to charge you like $16 to read it. Like that sucks. So you can look on something called archive. Never with the chalk. You can look on something called archive. And this will have preprints. So this is what it looks like when it's been accepted by the publishing company, but before the publisher does anything to it. So it's still the property of the author, and they will post it usually for free. So you can read the paper for free. This doesn't look well. It doesn't look pretty. It's not typeset on this, right? Doesn't have the nature at the top. Okay. All right. As you go through Google Scholar, look at how you format the search, right? Maybe you want to look at black hole research. You're really interested in it. But you might need to do something like put black hole into quotation, such that black and hole come right after each other. And that way you don't get something about like black sea, holes in the subsurface of like the Aral Sea, right? As you can imagine, any combination of these words might not automatically come together. Maybe you don't want to see a paper from 1866. So you say since, 1990. So familiarize yourself with that if you want to use that property, whatever it is, make sure you understand how to use this tool. Okay? Searching by date gives you more recent information. That should be obvious. There's 3 major types of science papers. Almost everything you'll read is a research report or a letter. Some of them are review articles. These will be significantly longer and tend not to actually hold a novel result. They will be, demonstrating the state of the art. They will be talking about what we have learned in the past 30 years or summarizing a new field. So maybe you have something that's on gravitational wave detection, relatively new field. It's probably going to be like 70 pages long. It's going to give you history, all these different parts, and it'll be wonderful to read. Really nice. The original papers, these research reports, not always nice to read. Some of them are nicer than others. The one that you have in front of you is a great example. This is a science paper, and I say this with a capital S. There's also nature papers. These are really nice to read. These are some of the highest, most important types of paper, this publishing company, in all of science. So whether you're doing anthropology, whether you're doing human psych, whatever it is, you publish in either of these journals. Wow, good job. Majority of publications do not go to these journals. But because they are so credible, because they are usually reserved for high impact work, they are also read very broadly. So they will be written for the audience, which is a broad, scientifically literate audience. That is you. You are not experts necessarily in every field that you'll find, and yet you should be able to read the paper in front of you. Mostly because Mars exists, that there is such things as atmospheres, water vapor is a thing, right? That'll all be explained, hopefully, in a good paper, right? Okay. So if you start in either one of these, let's say you start in a science journal or you start in a nature journal for something that you're really interested in, you'll usually get a really good summary, both of the state of the art, really briefly why this is a great advancement, and also what the advancement is. Okay. And then if you found one that you like, and you want to find others that are similar, look through the citation. Right. This is cited by 49. So you can look at people who said, oh, that paper was bullshit, right? And you can go through and see, oh, there's really contentious here, right? There's 200 people, and of that, 50 of them agree, and 150 disagree, right? That's what citations do. Or when you're reading through the paper itself, and you're looking through the references, and it says, we've known this since 1970, Bergdahl et al., 1931. You say, oh, what's Bergdahl et al. 1931? So you go to the references in the paper you're looking at, and you see that science is a story, right? It's not necessarily linear, it's not a very good story. You're going to read it to your kids, maybe if you wanted them to go to sleep. But it's this complex web of different people all looking to understand what we know about the world and beyond. Okay? Questions on finding paper? You can do this? Not necessarily, but you'll practice.
Over the summer, I heard like some PIs were like referencing different research papers based on like their impact.
Yeah.
And there was like a rating system in this, but I didn't go into detail with them about what that rating system was.
Yeah. Usually we would use citations. You know, the number of people who cite it tend to give you your impact factor, but sometimes you can get more meta with it, and you can figure out whether or not it's in a high impact journal, how many other high impact journal pieces came from this, etc.
Is that what the H index is?
H index is for people. H index is pretty fun. It's kind of garbage. So the H index is constructed like this. This is the number of publications. And this is the number of citations. So let's say you have a really, really important paper, like you just demonstrated that the speed of light is a constant. Your name is Albert Einstein. Okay, you can find that on Google Scholar, by the way. It's marked. You can find Einstein's H index. Okay, big number, huge number, but only one paper. He has more than one paper. Don't get me wrong, but I'm saying this contributes one paper. Okay, and then maybe you don't really do that good work. Like a lot of the work you do has to do with whether or not tennis balls are fuzzy enough for cats' tongues. And that's like a really niche topic that no one finds interesting, but you publish like 3 times a year. So maybe you're out here, right? Right. So maybe you struck gold once, or maybe you work really hard, but no one really cares, right? These are both examples of a low H index. So this doesn't make any sense, because the H index is constructed as basically a line like this, which is an intersection point between these two numbers, which says how many papers do you have with that many citations. So if you have 10 papers, each with 10 citations, you have an H index of 10. If you have 20 papers with 20 citations, you have an H index of 20. So if you have 100 papers with 100 citations, that's pretty good, right? That makes sense? H index of 1 is what you have when you've written a paper. You all maybe leave undergrad with an H index of 1. You'll all leave grad school with an H index of 3 or 4. Maybe you get lucky. It's like 18, right? Woo! Amazing. Do you have to be a first author? No.
Oh, so like the first year or something?
No.
Oh,
Just be on the paper.
Oh, sick.
You want to pump those numbers? I mean, they don't really get you anything, right? I didn't get a salary bump for your H index, but you might like it. Might get you through the day, and anything that gets you through the day is worth paying attention to. Yeah, I don't do that. Yeah, come on.
That's not good.
All right, let's look.
Oh, you're gonna.
Yeah.
Yeah, of course, we have time.
Okay.
We have to break up the monotony of me talking all the time. That's the worst part of this class. All right. So you'll notice what I have here. You see that? That is Google Scholar. So we can, what's that? That makes sense? So we go to Google Scholar. Oh shit, sorry. It's bookmarked here. And when you build a profile, which I encourage all of you to do if you're even considering staying in science, not even going to grad school, just staying in science, just because it's easy to find the stuff that you're interested in. And they developed this feed recently, which I really like. They understand what I've published. They've understood the stuff that I click on constantly. So they're going to show me papers that are just hitting right away. Yeah.
So it's an actual account you signed in for. Okay. Okay.
We'll go to my profile in a second.
Okay.
But you have to create it, right? You have your own Google, that's fine. But you have to identify yourself as a researcher at such an institution. And then you later on, you'll get an ORCID ID, which will be like your one signifier on actual papers that distinguishes Mike Smith from Mike Smith, right? There's many Mike Smiths in the world, believe it or not. And they're not all the same person. So some of them are both in the same type of science, which is really funny. Mike D. Smith, Mike R. Smith. You're like, oh shit, right? So you have to know the difference. Okay. So you can see here, right? What's the first thing I'd do if I wanted to read this? I'd say terrestrial planet habitability, insights, craters, atmosphere. Right, and I say, huh, that seems interesting. Let's click that. Oh, look what comes out. Abstract. Okay. And now I can read the abstract. You know, does this seem garbage? Right? Okay. Let's see if I can do this properly. I should have brought my pen. Now, what am I missing here? I don't have any information about how well cited it is, right? This is hiding information really about the full author list or anything like that. But if I'm very curious, right, this is a brand new paper. So citation can't tell me anything. There's no way to have it already been cited, right? But I can look in these references and I can find out more stuff maybe by this author or by someone else. Okay, let's look down again. Okay, so I see magnetic pilot boundary. I'm like, I don't care about that. What else is coming out? Ooh, orbiter camera data. I love pictures, right? So I'll go and I'll click on that. Or, you know, this is looking at magnetohydrodynamic simulations. I hate simulations. Ooh, so I don't want to read that. This one over here is oscillations, simultaneous observations. Okay, I like that word. That means it's real data and probably someone's observations of the said data. So I'm a data guy, right? And I really love looking at data, understanding it, and seeing how it influences models. This here, I could do without. Right? It's necessary. Modeling is necessary for science, just like instrumentation is necessary for science. I just can't do any of those things. So I'm not going to read a paper about it. Okay. Maybe you look at this thing here and you say dust storms in the lower atmosphere of Mars. And you're like, oh, that sounds really fascinating. But then you recognize this name. Like, oh, I hate that author. They never know what they're talking about. Right? And that's a true story. Sometimes you'll read something and you're like, oh, this person just claimed that they found metal spherules that are from outside of the Earth, that they're interstellar pieces of metal that they found on this beach. But this guy is not a planetary scientist and thinks that aliens exist and is not a real, like, astronomer. So you say, as soon as you see that little last name, you're like, ugh, all right, you don't read the paper. Yeah.
No, no.
Do you want to know what it is?
Yeah, I think I heard about someone's thing.
Yeah, it just hit the archive. This has been on the news for a while, but the guy's there are some times in life where you get to a certain position and you live in a place that has a name, and that big name can overshadow your real qualifications. And the news has a vested interest in getting people to click or to buy. So they have no responsibility at times to report the truth. Science is a discussion between you and I, or you and the person that you're reading the paper in. A lot of times we will see scientific discoveries. For example, there was this big consortium at the Large Hadron Collider in Europe, where they seemed to see something moving faster than light. And they were very perplexed. They didn't know what was going on. So was something going faster than light, as all of the media reported on? No, in fact, it wasn't. But they put the paper out there because they're asking the scientific community, hey, listen, all 700 of us couldn't figure it out. Is anyone out there going to be able to help us? Right? And sure enough, the paper hit the archive. It was discussed by many, many scientists. And a few months later, they figured it out. Right? That's how science happens. It's peer reviewed, people similar to one another talking about the process of science, right? So if I'm, studying the atmosphere of Mars, I'm not going to read an LHC paper and write to comment on it. Oh, I think you miscrossed some wires, right? That's not helpful. I don't understand what they're doing, even though we're both semi-physicists. So he is a semi-physicist. Anyway, I'm gonna not rant too much, but here's where you find archive. And the archive is fantastic. Okay, this is probably where you'll end up looking at most of the stuff that you're interested in. You have astrophysics, and you have all of the different subfields of astrophysics. Okay. You have condensed matter. Okay. You have general relativity. Okay. You have high energy. Fine. Mathematics, nuclear physics, and then you have down here physics. Okay, so maybe you really, really like classical physics. You're like, hey, how can I solve that 700-year-old problem even better? Right, that's right there. Okay, maybe you need a little fluid dynamics. You're like, it's been a while, I want to see how people be doing it these days. It's right here. Okay, or maybe you actually want a job, well-paying job. You're like, okay, let's look at medical physics. What does that mean? Right? What is like the newest, hottest thing in medical physics? So that's all here. This is just physics. So if I scroll down, you'll see that there's other fields. You won't go into them. Anyone here not a physicist? Okay. That's fine. You're okay. It's okay if you're not. You see all these different types of papers? So this form of communication is extremely valuable, right? Because this is the place that the newest science hits for a particular brand of science and gets discussed before it makes it to print, right? So the idea is you put it on here and you hope that if there's an error, someone will catch it. So let's look here at this paper from, oh gosh, where would he have put it? All right. I don't know where it is. Let me just search. His name is Avi Loeb.
But it's terrible.
It's fine. I don't have a problem with his name.
So he was credible once, and then like now he's like
Yeah.
talking about things that he has no like reason of business.
Yeah.
Got it.
Yeah. So one of the things that ends up happening as you get older.
Yeah.
Okay, I don't remember where it is. Oh. Something like this. Is it this one? An ocean expedition. I wish they would do this 2022. Is this in reverse chronological order? May 2023?
No.
Okay, I'm not gonna be able to find it live, but I can post it for you if you want. What was the point of what I was saying? Yeah, sometimes you'll see a name about a scientist who just is not generally liked in the community. Doesn't do good work. There are certainly people who continue to publish who have done bad things. Right? They can't be removed. Yeah, bad things. Academic misconduct, right? Like literally fudging results, creating data that doesn't exist, blatant misinterpretation of data and or past results, verbally or sexually harassing members in their community.
So like skewing results by doing that better? Or
Yeah.
Like, was it,
Or both, but it's usually the latter, the first one.
I think, wasn't it like, either the chancellor or the president of Stanford was like, had to like actually, I guess, resign because like somebody freshman year of like the newsletter.
Yeah.
Just investigated like all the stuff that he like had all these papers on and like how he fudged everything.
Yeah.
And like everyone knew, but they just never pursued it.
Yeah.
And so now he's like taken down by like a 18-year-old.
Yeah.
That like just happened.
So science is done by people, and people are fallible. You know, we always want to, generally speaking, assume that someone doesn't know what they're talking about before assuming that they have ill intent, right? But if there are repeated patterns, right? Like if someone touches you and you don't want them to touch you, right? And you say, hey man, don't do that, right? And they never do it again, that was a misunderstanding. But if they do it over and over, it's malicious, right? That is the difference between scientific writing, which has integrity. Oh man, I fucked this up. I published it too early. I should have gotten another look at this. Or I didn't know that repository was out of date and I was using incorrect data, right? That's fine. There's nothing wrong with it. That's a process of doing science. It's iterative, right? You always are replacing the status quo with something slightly more improved. You might upset someone. You might find out that, oh, actually, the way I did it, I thought that I was replacing the status quo. I did it wrong. Okay. You write another paper. Now you have 2 papers with citations. Okay. That's okay. There's the whole discussion about it, right? But there are, there's bad eggs in every community. Not as many as like the police community, but it's fine. Okay. So let's talk a little bit about Google Scholar. Oh yeah, you wanted to see mine. Here's my profile. So they have citations by year. So you're thinking, oh my God, he really fell off. Well, that's because it's not done yet. Don't be mean. Okay. There's the H index, it's 28 since 2000. Oh no, that's all. Since 2018, it's 27. So that means I have 28 papers with 28 citations. But in Google Scholar, you'll notice something slightly different than NASA ADS. Let me put that up as well. NASA ADS uses different criteria for what counts as a citation. I know. And ADS is the Astrophysical Data System, even though now it has papers. So here you'll see that there are some, these papers, right? It's a big paper cited by a lot of people. But that's not the case for all of the papers. So if I go into the year and I sort it by year, you'll see, okay, this is a journal. Good. This is a journal. Good. This is a congress. In a congress, you can think of the word conference. So this is a talk. And it may be the case that this talk cites another paper. NASA ADS will tell the difference between that because this is not refereed. This was not submitted and then someone signed off on it, right? Whereas these are refereed. So these citations count more than this one. Does that make sense? Okay, so it's all fake. It's all fake. If I look here, right? How do I do this? So if I look here and I see something like this, loss of the Martian atmosphere to space. Oh, that sounds interesting. Cited by 242 people, and it's only been 5 years. So I think about that and I start to think, is that good or bad? Yeah, good idea. I don't know, right? I don't have any idea about this yet. You'll have to understand that yourself, right? Every field is slightly different. Some fields have lots and lots of people in it, and therefore when there's a new paper, lots of people are reading it, they're either getting inspired to work more on that topic or to tear it apart, right? Some fields are really small. Like I made this example about cats licking tennis balls. That could be a field where no one else publishes in it. So if you have a very niche topic, expect low citations. If you have a topic that is very well, regarded throughout all of scientific community, like what does the mineral on Mars look like? you're gonna get a lot of citations. You'll notice that the first one, Mars, second one, Mars, third one. What is that? Extrasolar planets. Oh, that's a hot topic. Okay, so that has 210 citations, but is almost older than I am. That's what you're saying. No, that's a joke. Okay, so you're like, well, that really got outstripped. So this was really hot when it came out, and maybe it petered off. Maybe more papers were written, and now it's not as important a paper, right? But the citations only ever add, right? So the question, what's its longevity? Yeah.
I don't wanna like disrespect you, like, class.
I mean, you're an adult. You can do whatever you want.
I have something to do, instead of-
I mean, you should do it beforehand. But that's the shame you have to carry inside your heart, you know? Okay. Now I don't want to. Yeah. Do you want to share this? Is that what you're asking? Okay, I don't want to share it either. So here's the 2019 paper. Okay, and so maybe you just look in here and you do a comparison, and you say, wow, this one here doesn't really look like it had as much gumption as this one did. They're almost the same year, 100 less citations. So either this paper really sucks or this paper is really good. Yeah.
Oh, it's no question. The citation,
No
like,
such thing, by the way.
what's, you get cited, does that mean? When you get cited, does that mean like, another scientist read it and like reviewed it? So
Not reviewed it, referenced it.
Okay.
So the citation means that, Kobe 2023 demonstrated that coming to class with coffee is the preferred method. And then Paolo references, in the future, we will make a similar computational error. You right? You see?
Nice.
Okay. See, it's topical. You're staying engaged. So you can't really tell, right? You're learning, and this is a skill. You won't know off the top of your head whether that's too many citations, whether that's too few, but you'll build up a feeling in whatever your field is. You'll begin to read more papers. You'll begin to understand what are the important papers, right? So for example, you start seeing a name over and over, you're like, huh, that person seems important. So let's have a look here. Any names stick out to you? Not mine. He called me. Maybe let's do a plus here. I know, I'm trying. Is that better?
Yes. Yeah.
Yeah. Where how many times do you see Joukowsky? A lot, right? Yeah, so Joukowsky. So he's on the top two, first author. Okay, anything else?
Yeah, I think there's a third one that comes down.
Here. Yeah, that's important. You can't tell, but he's at the very end of this one. So he's the PI for the Maven mission. They're studying the escape of Mars to space. So there's a couple places that are like reserved for the coolest in the group. The first one is the first one. Second one usually is like the second most important author. Sometimes the third really matters. But the last author is usually a sign of respect. So it's like, when you're watching the movie credits and it's Tom Cruise, and Jennifer Aniston, and then it gets to the very end and it's like, I don't know, some artist, some dude, but it's like some old dude, like Tom Hanks, right? And it's like, why does Tom Hanks at the end? That's the nice spot. Okay, so that's the same thing happening here. So Joukowsky's name is all over here. He's a very well respected and well published author. And you'll see that when you just start seeing his work. You see other pieces where you're like, wow, this Avi Loeb guy seems to be really getting a lot of hits. Look into the citations themselves, right? So if I go here and I look, right, look at all these people. Wait, where'd it go? I say, okay, cited by 242. So let's go into that. Okay, and we're gonna see all of the types of people who have cited it, right? So the first thing to note is that there aren't any like red flags, like Joukowsky's paper on climatological evidence is incorrect, right? Which is how you would respond to a paper like this. If there's a discourse that's being had, there's usually a comment or a statement about that. So you'll see something that is literally going to say, such and such a theory. And then someone else will respond, comment on such and such a theory. And then you'll see reply to comment on such and such a theory, right?
So it's like, if someone disagrees with you, they also publish
Yes,
the article?
yeah. Controversy is good for your HMS. It's bad when it's taken out of context, right? If someone comes along from People Magazine or Us and says, "Oh my God, this means that we found life on Europa," you're like, "No, we're arguing about whether or not life could exist in this subsection of this type of rock." They're like, "So you found it," right?
So when they challenge the paper, so we can put on it, review.
Hold on, say that again.
So when they challenge the paper or something, you want to say a review of the paper, it's like.
Okay, so the paper reading and writing process is a little tricky. Let's say I write a paper. Okay. Write a paper, and Giselle is the publishing company. Okay. So I give the paper to Giselle. And you give the paper to Qatar, who's gonna read it. And she's gonna give me feedback. Now, since I don't know who she is, and Giselle selected her, and maybe she also gives it to Paolo, right? And she looks at these two reviews. And she says, okay, these peers reviewed it, and they had this feedback, and either the feedback was, make such and such a change and accept it, or maybe it's garbage and throw it out. And so she interprets their reviews of it, and then she gives it back to me, right? And I go, oh, okay, I'm gonna make the changes, and then she says, okay, I deem this eligible for publication. So she's a gatekeeper, that's okay, we need a little gatekeeping in science, but there's a conversation, kind of a hidden conversation about the quality of the work, right? Then it comes out, and it stands on its own, right? And then Kobe's like, oh man, they fucked up, they didn't include, bada bing, bada boom. So he comes along and he's like, oh, well, you give this to Giselle and you say, hey, stapler, and then she passes it to different reviewers and they look at it and they say, this is stapler. And so now these both exist in the public frame because science is done for everyone to be able to see. All right, so first you read this one, and then you read this one and you go, oh, okay, and you make your decision. Okay. Yeah. And we'll do that. We'll practice controversy, not this week, not this next week, but in 2 weeks from today, we will do controversy in science. Okay. Are we done with this? This is finding a paper, reading the abstract. God, that went a little long, but I don't care. Sometimes I just talk. Sometimes I talk. Okay. Let's read the abstract. You're going to be reading the abstract and the title. Titles help you. Sometimes they don't help you. What you're going to be doing here is you are going to look for key phrases. The first phrase is usually a topic sentence. You should practice this type of writing, which if there's a paragraph, the most important sentence comes. What? First. The first sentence is the most important sentence. When you are writing scientifically, you need to be prepared to write as though they will only read the first sentence from every paragraph. If that feels weird to you, yeah, it's because scientific writing sucks. Okay, it's not narrative. As you read through here, okay, you'll see the vertical distribution of water vapor is key to the study of Mars's hydrological cycle. That's your topic sentence. To date, it's been explored through global climate models because of the lack of direct measurements. However, this is an inflection point that you want to pay attention to in the abstract. This is telling you that a change is coming. That this paper has done something new or identified a problem with the status quo. These models assume an absence of supersaturation. Now you might think to yourself, what's the saturation? I recommend if you have a paper like this, print it out, you underline, or you use a highlighter, because you can look where it's at, right? You can find out what these things mean so that we can understand what the rest of them are talking about. You see that I did this online. I read almost exclusively online, because I like trees. And so I just put this, right? And I know to myself, something was funny about this. Does anyone know what saturation is? Okay. Yeah. the amount of water something holds, exactly right. So if I have a towel and I put it down into a puddle, it gets filled with water. And so you say, okay, that doesn't have anything to do with the atmosphere. Well, kinda. Right now, we're in a deserty area. Kind of humid, it's kind of dry, it's not very humid. So the air is not stocked with water. If I go to Florida, it's more humid. If you get to 100% humidity, what tends to happen? What? No, what tends to happen? What climatological phenomena tends to happen at 100% humidity? Rain.
Oh, okay.
The rain, so when you think about saturation, how much water can be held? Well, if you get to the limit of what can be held and you put more, guess what happens? It comes out. Okay, so when we talk about holding, it's the same idea. You put this towel into the water, you try to soak it all up, but the towel is small and the puddle is big. So now your towel is dry. Okay, that's the idea of saturation. And what they're saying here is very important. These models assume the absence of supersaturation. Supersaturation would mean what?
A lot of sex.
Excess saturation. That means that you can go above 100%. Because on Earth we can't, or we typically can't. Right? Once you get to saturation level, you get condensation, you get rain, you get a different process, sublimation of bringing the liquid water in the air out. Right? Okay. So then they report. Here we report. So this is what they've done. And now they're going to walk you through the things that they did. Okay. They provide evidence for the presence of water vapor in excess of saturation. Wow, crazy. Right? Everyone stop depressive. Well, now this is depressive. Okay. This result, and this is what they're going to tell you what's important about, contradicts the assumption that atmospheric water on Mars cannot exist in a saturated state, directly affecting our long-term representation of water transport, blah, 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 blah. Okay, let's break that down. They're going to tell you about the state of the art. They're going to tell you about a problem with the state of the art. They're going to tell you what they did, and they're going to tell you why it impacts the world. So generally speaking, an abstract and a paper will look the same way. And I'm going to show you this a number of times throughout the semester, but you're going to see it right here for the first time. Papers start broad. State of the art. Okay. Issue. Okay. How they contributed to the issue. The result. How that result contributes to the state of the art. And how that influences our understanding of the universe. So it's a little bit like a funnel, right? You take this broad topic, why should anyone give a shit? You narrow down to your contribution, and then you put it back into the context of why should anyone give a shit, right? Make sense? Okay. So this is what writing a nature abstract looks like. This is just the same thing that I've said before, but this is what nature puts out. You know, if you want to publish Nature, you have to write in this style. And generally speaking, it's a good format. It's very readable. As you go through this, maybe we'll have time for this. As you go through this, you'll notice how well written this paper is. It's written for a general audience. Right? Okay. Next step. What's the step after reading the abstract? Forgot. Figures. Figures. Okay. Why do we read the figures before reading the text?
What result? What numbers are significant?
Okay, kind of, yeah, I think we're on the same boat, but we might not be saying the same thing.
Yeah, you could see how they try to quantify what they got as results. So like what they're measuring is most likely going to be in some sort of scale. So you can get a better idea about what are they trying to say, or like their results. If they have results, how do they quantify those results? And most of the time it's either a table or a graph that's being plotted. And like humans, like
I might say this slightly different. I think we're sort of speaking around the edges of the same thing. I would say that the data
is king. Okay, or queen. The data is the most important part of any scientific paper. Because our interpretation of the data is independent of the data itself. Let me repeat that. Our interpretation of the data is independent of the data itself. The data will not change, but our interpretation can. So your interpretation can be straightforward. It can be, how do I read this? Versus a model that uses that data to predict or understand something about the future. Those things can be wrong, but the data does not necessarily change. So as you go through a paper for the first time, you are trying to understand the data independent of whatever they're saying. Because when you first read a paper, you should be skeptical. And you should consider yourself extremely skeptical when reading, such that they convince you, right? To be a good scientific paper reader, you have to be thinking, okay, does this really make sense? Does this contradict what they said before? Does this supported by the figure that they're claiming this is in reference to, right? So generally speaking, you look and you say, okay, even before you read the caption, cover up the caption and just look at the data. What the heck am I seeing? Okay, so this is something about time. This is something about how much water there is. This is something about latitude. And I'm looking at this picture and I'm saying, okay, well, as the seasons went on, it looked like there was more water in the northern hemisphere. That's what I read. And then I read the caption. Okay. Test water columns are superimposed to indicate the corresponding activity of water vapor during the time when the measurements were taken. Okay, that doesn't really tell me. That sort of tells me what the different axes are. But if I read in the paper, my interpretation was correct. Now, of course, I've read this paper a bunch of times, so that's not fair, right? But you would do this yourself. And you're going to check yourself compared to what they are presenting, right? So we want to think about what all these different pieces mean, right? What do the vertical axes mean? What does the color mean? What is the primary thing I took away when I read it? So maybe if I have the paper in front of me, the first thing I'm doing is I'm saying, what the heck is this thing? Oh, Sebastian, that's not a word I know. So maybe I write a little note and I go and I open up Google and I write Elsebas Mars. And it turns out that's a thing. Okay, I learned about it. Okay, column density. I don't know what that is. I looked that up. That's how much water it is. Oh, I got that now. Okay. And maybe at the end of this, I say, I think, I write on the paper, I think this shows water vapor in the northern hemisphere with time. Okay, that's my interpretation. And then I read through it and I see, oh, that's exactly right. Or they didn't draw that same conclusion. Oh, that's funny. Right. Okay. Does this process leave you questioning? Does it leave you mistrusting of your interpretation versus theirs? At first, you should feel like, I don't really have a lot of experience. You'll get better and you'll understand better how to interpret papers, right? Especially things that are not in your field. But I can read a paper that's about rocks and be like, this doesn't make any sense, right? Because if you know all the words, have an understanding of how the physics is supposed to fit together, because they explain it to you. You can say, are there logical inconsistencies? This picture says that, there's water in the northern hemisphere. If in the text, they say water appears in the southern hemisphere, you would say, wait, what? Right? That makes sense?
Yeah. Does that happen frequently where you looked at their data and then you draw different conclusions from what you've seen?
Yes and no. We'll talk about this when we talk about controversy. I might give a different paper, depending on whether or not you guys just want to hear about my life. Okay. Yeah, my life? Yeah, sure. All right. Reading the conclusion in the research article is straightforward. It should have something that says summary or conclusions. That's how you find it.
How do you find the summary when you don't have them marked as such? Well, I already told you about. That's pretty cool set it to. You find the first line, right? And this will help you sort of navigate the paper at whole points of this. So for example, let's say I'm reading through this and I want to understand it better. I'll read the first sentence. So maybe this third paragraph, it says the water vapor profile data set presented here was extracted from SpeedCam. They talk about SpeedCam, solar occultation observation. So now I know where to look for information about the instrument. That's paragraph 3. Whereas if I go over here, the existence of supersaturation has profound consequences for our understanding of the basic mechanism that have regulated the water cycle throughout the last billion years. So that's the ramification. That's the reason why people care. That's the second to last paragraph, right? I'm just reading the first sentence, and it's giving me clues as to what is in the paragraph, right? So you can do that, right? You can be writing notes. You can write them in the margins. You can write them on your own paper. But all the while going through writing about the paper, I would recommend you keep notes. And they don't have to be notes that you turn in that have, really clear, cogent thoughts. They can be like, what's Mars? And then you go and you look at it and, I remember what Mars is, right? It's a process that you want to remember. Did any red flags go off along the way? They said this really early on, and at first I didn't understand it, but then I read the paper more and I got it. So I'm going to check that one off. I do that all the time. First, I'm like, this is stupid. I'm going to write them a letter. And then I read the rest of the paper and I'm like, oh, I get it. Right? Sometimes you really get carried away. You think that they fully misinterpreted it. And then you sort of read through all of the ramifications. You're like, oh, they're talking about this specific thing. I get it. Right? Okay. Your writing should reflect that. Right? You're going to be practicing writing topic sentences. Do not bury them deep in the paragraph, but we already said that. And do the conclusions that you reach agree with the interpretations that they have in the conclusion. All right, that's the thing you're asking yourself. Is this a credible paper? Okay. Could the paper be wrong? That's the best. There is no better feeling in the world than being right and the author. Okay, let me tell you when this happened. I'm going to tell you about personal life. We're not necessarily going to get through all these. In grad school, I started working on this mission, Maven mission. And we had a new instrument that was going to Mars for the first time. It was doing something slightly different, and it had a different capability than what had been seen before. And I saw this thing. And I was like, this thing's really weird, right? And I was like, that looks a little bit like this other thing. And so I said, this thing looks a little bit like meteors on Mars. And someone else who had written a paper about 5-6 years earlier said, oh yeah, we know there's meteors on Mars. I don't know. I'm seeing a lot less than you're seeing. They're like, well, calm down a little boy. Okay, it's in grad school. I don't know what the fuck you're talking about. And I said, no, I don't think you're seeing meteors. I think what you're seeing is something else that I can't explain yet, but that's not right. And they were like, you don't know. We wrote in science. I was like, I'm pretty sure you're wrong. Guess who was right? Okay? Because I didn't believe their results because of new evidence. That happens. Sometimes you revisit an old paper, you know a little bit more about the situation now because of whatever instruments come along. Like, kind of looks like garbage, Okay. But you have to hold on to that skeptical feeling. And there's an art here. You can't be too skeptical and never believe anything, and therefore never get anywhere, right? Science is a foundational topic that builds upon the work of others. But you also have to know how good your bullshit meter is, right? Turns out that other thing they were finding was a different real phenomenon. But they ascribed it, the data was real, remember? The data wasn't fake. But they ascribed it to the wrong phenomenon. So then we wrote a paper in 2019 explaining what they were seeing. And later in 2021, someone came along and verified what we had found. That the thing that they were saying was a completely different phenomenon. Right? That is the process of science. Now, we won't go through that because it's very complicated ionospheric stuff, but it's possible, right? This is like the active process in the 15 years, moving from, I think we see this thing. Now we don't really see this thing. Oh, it's something else, right? Okay. Questions? Okay. So with the same technique that you read the summary, then you start reading the paper. Okay. And you can be a little bit willy-nilly here. You can be a little bit quick. So sometimes, you don't have to read every single sentence to understand the scientific importance of the paper you're reading. Maybe they're talking about the instrument and you're thinking to yourself, man, I really don't care. I trust that they built the instrument well. I just want to know what the results are. So maybe you just read a few of the paragraphs at the beginning, and then you start reading some paragraphs about the results themselves and the interpretation they draw. That's okay. I'm not going to hold your feet to the fire on that one. Okay. If you're just getting into a topic, the intro is going to be your friend. Read that. Specifically, look for references. Right? The first time we ever found Mars was 1391, right? And you look at that paper, this is the person who found it, right? Mars wasn't found by a person. Does everyone know that? Been around since ancient times? Because you can see it with your eyeball. So they named it in ancient times. Which ones are modern planets found in modern times requiring telescopes? With named people. Yeah. Pluto's barely a planet, but yeah, good points. Anything else? Neptune, very good. And
Could they see?
you?
Wait,
I don't know.
yeah, I don't know this, but could they see Mercury? Like at all, or was
You
that,
can see Mercury. You can see Mercury.
Like,
Yeah, but it's got to be the right season. So you have to look right before the sun rises, and Mercury has to be in exactly the right configuration. And it's going boop, 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 across the sky. What?
You can see that like quickly or no?
No. You have to watch it every year.
Oh.
But it moves quickly compared to all the other planets. It's the fastest planet, right?
right?
If you see the word should in the introduction in the text, this usually indicates a hypothesis. So maybe you have a part in the text where they say, the presence of water in the northern hemisphere should indicate that saturation is occurring, right? And then you look at the data itself and you see, does it support that hypothesis? Remember that, your very first semester of science ever, they were like, well, that's actually an important thing that happens. People will posit a hypothesis, and then they will look at the data, and they'll see if the data supports the hypothesis. And if it does not support the hypothesis, they will try to explain it in one way or the other. And sometimes they'll say, I can't conclude anything from this data, right? That's a null result. Those get published, although they get published a lot less frequently, which is why sometimes there's like too much bad science in the field. Okay. And if you see something like in the conclusions, for example, that says, outstanding problems should address whether or not having 3 Big Macs a day is a great idea, right? You could be like, maybe I'll do research on that, right? I have a personal, McDonald's card that I could figure out whether or not that's good for the course of this semester, right? So shoulds here, these hypotheses, sometimes they'll get closed in the course of the paper, and sometimes they'll lead to more problems, right? And maybe this is the place that you want to go for your next paper, right? Or maybe this really gets you thinking and you're like, hey, this thing is similar to this other thing. I wonder if someone's thought about it that way, right? Okay. So you take away the most important parts, asking questions to the class, that is to say to your partners in class, or to me when something isn't clear. And, I don't know if anyone uses Slack. They just use it to find times to talk to me. What do you guys use to communicate other than your mouth and phone? What's that? Group me? You have a group me?
Not for this.
Some people. Okay. Well, use a group me. No.
It'll be helpful. Okay, questions? Okay, so typically I would have had you read this paper, but we're kind of running out of time. So I'm gonna have you just look at and annotate just the abstract. Okay, in a way that's sort of similar to this piece here. You know, highlighting key topics and phrases that give you pause, discussing what you think it means, right? And maybe go through the first figure while we have some time. And then we're gonna talk through how to use a telescope. Okay. Don't put it at the sun. Don't put it at the sun. What happens if you point it at the sun? Not you'll go blind. It will go blind. You'll ruin a very good telescope. Yeah. Yeah. The sun hot. If you really want to put the sun, you have to use the phone. Use the sun. You just really want to, even if you just right now, even if you just looked up at the sun, you could cause permanent blind. You just stare like this. You know, this is why those TikToks about grounding and sun staring, very dangerous. Do not stand out in the grass and stare at the sun. I cannot urge this. Yeah, some people have decided that it's a really good idea to stand out in the grass with no shoes on and stare at the sun.
Grounding?
You've heard of grounding before?
That was no shoes.
We're not gonna get into it.
I'll get into it.
Let's focus first. First, annotate the abstract. I'm gonna grab the telescope and I'll be right back. Annotate the abstract, please. If you need to use the restroom, this is the right time. We're gonna meet, you know, at like 5:30 to do the telescope itself, okay?
Where are we?
But if you need to use the restroom or get coffee, this is the time to do it.
Yeah, one buck. You over there, you don't want to sit with me. We could fit 3 chairs right here. Yeah, 1, 2, 3. You like ass to ass. Either 4% and a half. It's thirst. And I'm a premium in the show, you can tolerate it, but just like that.
Probably should have paused this recording. And then I'll have it snack.